Hello, so this is homework 1 part D, and we're going to be kicking it off with deriving the relationship between vapor and liquid compositions for a binary mixture of constant relative volatility. And what we're going to be using is the benzene toluene mixture from part C, and we're also going to use the code, and we're just going to add a little bit more to that. Let's just get started with defining our general equations. So first what we're going to have is x1 equals k1 times x1 and y1 equals k2 times x2. And also I'm mentioning relative volatility. To simplify, it's going to be alpha, which equals k1 over k2. Now that we have our equations, we know that this is a binary mixture, and to start off we're going to use the equation 1 minus y1 equals k2 times 1 minus x1, and from here we're just going to go ahead and divide over our y1, and we're going to be left with k1 over k2 times x1 over 1 minus x1. Sorry if I'm coughing, got a little cold. And from what we know, now we have our relative volatility in our equation, and x1, 1 minus x1, then we're going to have our y1, 1 minus y1. And our goal now is to isolate this y1. So how are we going to do that? Well, we go ahead and multiply over. So we're going to be left with x1 times 1 minus y1 over 1 minus x1. And then if we work out this equation, we're going to go ahead and multiply this through, and we're going to move this over. So 1 minus, or y1 minus y1 times x1 equals alpha x1 times, or minus alpha x1 times y1. And now we want to separate these y1s, and we want to make it y1 equals. So how are we going to do that? We're going to go ahead and move this over. So we're going to have there we go. And we're just going to separate this out so we have a nice clean equation to work with. And y1 will equal alpha times x1 over 1 minus x1 plus alpha times x1. And we're going to use this equation to generate our XY diagram and just see how the average relative volatility is affected. This is the coding section. So we have our code from part C, and we're going to use this graph to display those relative volatility values. So let's just get started and create our arrays. So we're going to have y1 equals np dot array, and we're going to have our y1s values, our vapor coefficient values, and we're going to have 1 minus 1, and this just essentially takes out that first value in the data set of the array. Go ahead and copy this to make for the liquid composition. There we go. So now we have our liquid and vapor composition arrays, and then we're also going to go ahead and get the average. And we're just going to plug in this equation right here. So we're going to have y1 times 1 minus x1 and divided by minus y1 divided by x1. Yep. Oh, I have to run all. Might take a second. There we go. So we have our average value. We're going to use this 2.49 here above. So we're going to go ahead and set our alpha. Oh my god. It's 2.49. And we're going to go ahead and add another fig dot add underscore scatter. And our x is our liquid. And then our y is going to be our equation that we found. So let's just go ahead and type that out. One minus x1s plus alpha times x1s. And we got that correct. And we're going to use markers to make it easier to distinguish. And then we're going to give it a name, const alpha. That should work. Yep. So there we go. So we have our values displayed, and this kind of just shows that our alpha values align with the plot that we found last time. So this shows our constant relative volatility values.